Let me talk about aromatic electrophilic substitution. Now, aromatic means that we're talking about aromatic rings, and electrophilic means we're talking about something that's going to be positive attacking the ring, which is going to be considered to be fairly negative. Alright, well, let's talk about what an electrophile and a nucleophile are, just to make sure you remember that. Electrophiles are species that are electron-loving, and they're attracted to negative charges. As such, they tend to be either positively charged or they have the need to fill an octet by adding electrons. So these are considered to be electrophilic type species. Nucleophiles, on the other hand, are positive loving. Nucleo meaning nucleus, and in a nucleus what do we have? Protons, so we're talking about positive charges. So positive loving species, and those are attracted to positive charges, and hence they're usually negative, like OH negative, SH negative, N3 negative. Or they can be neutral but have a lone pair of electrons, and that can be nucleophilic. So ammonia is also considered to be a nucleophile. Br-, Cl-, all good examples of nucleophile or nucleophilic species. Alright, well, let's talk about how bromine adds to an aromatic ring in contrast to how it adds to cyclohexene. So cyclohexene just has the one double bond in the ring, and we know that when bromine gets added to the cyclohexene ring, it adds in a trans fashion, and we get two bromines attached to the ring, one sticking up and one sticking down. So what happens is the Br adds to the ring, we get this brominium ion where the bromine is actually sticking up above the ring, the Br negative comes in from underneath, and we end up with this trans orientation of the product. Now, if we were to do an analogous situation with the aromatic ring, we might expect the same thing, where we would get addition of the bromine across one double bond like this. We'd have one sticking up and one sticking down. But that is not the case. That's not what we end up with. What we end up with is a single bromine attached to the aromatic ring where the hydrogen used to be. So that's what makes this an electrophilic substitution. The Br is actually going to substitute for the hydrogen that was initially here. So how does it work? Well, what goes on is that we have the FeBr3, and that actually forms or helps form the Br+. And the Br+ is what actually reacts with the aromatic ring. So the Br+ is an electrophilic species. It's positively charged. It's going to be attracted to the electrons in the ring. That's what makes it an electrophile. So the Br+ attacks the double bond of the aromatic ring. The Br attaches to one side, the plus goes on the other. Now at this point you might be wondering, why doesn't a Br negative or something negative come in and attack this positive charge? Well, what happens is that we now have a non-aromatic compound. Now this compound is non-aromatic because it's not conjugated. It goes single, double, single, double, single, single. So we don't have an aromatic system here anymore. But this ring will lose H+ and reform the aromatic system pretty quickly. So the slow step, I think, is actually the Br+ adding to the ring. The fast step is the H+ being lost from the ring so it can become aromatic again. But as you can see, what's happening is the Br is actually physically replacing the H in the final compound. Now this doesn't work just for Br+, it also works for other electrophiles as well, and we'll go through the list and talk about those different electrophiles. But the general mechanism is as follows. The E+ attacks the aromatic ring, and we show that by showing an arrow that goes from the double bond to the E+. Now when this happens, the electrons from the double bond are actually forming a bond between this C and the E. That leaves a positive charge on this C. Then what can happen is that the hydrogen plus can be lost as H+, and we get our electrophile attached to the aromatic ring.